So my name is Christian, and today I will be giving a brief introduction into altermagnetism, a phenomenon which has kind of been hailed as like a third type of spontaneous magnetization alongside ferromagnetism and antiferromagnetism. So kind of as just like an outline for this presentation, I'm going to be talking about like what exactly is altermagnetism, some of the challenges that are faced in kind of its study, and then some of the prospects that it has for future devices and applications. So first, what exactly is altermagnetism? To answer that question, it would be helpful to first kind of review ferromagnetism and antiferromagnetism. So historically, researchers would group types of spontaneous magnetization into either ferromagnetism, where you'd get all the microscopic magnetic moments aligning parallel to each other and giving you a non-zero net magnetization, or antiferromagnetism, where you'd have the magnetic moments align anti-parallel to each other, and that would give you net zero magnetization for the whole material. Another way you can think of the difference between ferromagnetism and antiferromagnetism is actually through the band structures, where for a ferromagnet, you'll see two distinct bands, one corresponding to the spin-up electron states and one corresponding to the spin-down electron states, in this case, blue and red, respectively. So because the two bands are offset from each other, at a given energy, you'll typically have more spin-up states filled than you do spin-down states. And this discrepancy is what gives you the net magnetization overall. Now, for an antiferromagnet, you actually don't see this splitting between the spin-up and the spin-down states. And because of this, at a given energy level, you'll typically have an equal number of spin-up and spin-down electrons, giving you zero net magnetization. Now, as of recent, researchers have been researching into certain materials, and they've found that there are some that don't fit this dichotomy. Materials like ruthenium dioxide and manganese telluride would display anti-parallel ordering in their magnetic moments, giving you net zero magnetization, which is typical of antiferromagnets. But when you examine their band structures, they would display splitting between the spin-up and the spin-down states, which is characteristic of ferromagnetic materials. And so because these materials would display antiferromagnetic ordering alongside ferromagnetic phenomena, these materials have been recently dubbed altermagnets. And by combining both properties of antiferromagnets and ferromagnets, altermagnets open up the possibility for applications to all sorts of devices that would typically require one of the two types of magnetism. So next, some challenges in the field of study of altermagnetism. Kind of the main challenge in researching altermagnets at the moment is that they're difficult to detect outside of theoretical calculations. So one method that researchers have used to identify at least materials like ruthenium dioxide is they would measure the anomalous Hall effect, which is essentially when you apply a current through a metallic sample, it would induce a perpendicular current within that sample without the presence of an external magnetic field. And the presence of this effect is what would help identify whether a material is altermagnetic or not. But the issue with this is that you can only detect this effect in conductive samples, whereas a lot of materials thought to be altermagnetic are actually insulating, so you can't pass a current through and you can't generate this effect typically. Another issue with detecting altermagnetism is that for certain materials, depending on the direction that you probe the sample, you can actually come across a region that's called or said to be blind to altermagnetism. So in the case of figure 5, if you were to probe this material in either of the yellow regions, you actually wouldn't be able to detect altermagnetism. Only if you probed it in the green region would you be able to actually detect the properties indicative of it. So in spite of these challenges, there are some prospects in the field as well. So a lot of the research that I had come across was actually dedicated to exploring methods of detecting altermagnetism. So one method that has been used experimentally is called angle-resolved photoemission spectroscopy, or ARPS, where essentially what you do is you shine a beam of photons onto the sample that you are going to be probing, and then you collect the photons that have been scattered and reflected off of that sample. Depending on the energy and the momentum of those captured photons, you can then recreate the band structure of the sample that you're probing. And by examining that band structure, you can then determine whether the material you're considering is altermagnetic or not. And another type of, or another like method that's been researched actually uses a very similar principle, but instead of firing a beam of photons, you fire a beam with neutrons, which would then allow you to actually interact with the spins of the sample itself. And by collecting the scattered and reflected neutrons, you can once again recreate the band structure and kind of determine whether your sample is altermagnetic or not. As for some of the properties and in device applications that have been noticed, one thing that's been noticed in certain, theoretically in altermagnets, is the Josephson effect, which essentially allows it to couple with superconductive materials and pass a superconductive current through it. This is of significance for two reasons. The first being that the current that passes through an altermagnet in this way actually is distinct from the current that's passed through a ferromagnet or an antiferromagnet. So that can actually serve as another method to determine whether the material you're dealing with is an altermagnet or not. And the current that's passed through, the second thing of importance is that the current that's passed through an altermagnet in this fashion can actually filter out certain types of spin pairs, allowing you to easily generate spin filtered current. Another kind of important application that's been noticed is magnetoresistance in altermagnets. So ruthenium dioxide, when applied to GMR setups, has been noticed or has been recorded to get up to 100% GMR at certain energies. And certain alloys of manganese silicon have been recorded to reach up to around 360% when used in TMR setups. And so by using altermagnets, you can get either pretty good numbers for GMR or standard numbers for TMR, while also eliminating kind of any downside that would come with having a net non-zero magnetization. And this is just some of the properties among the many others that are currently being studied. So in conclusion, altermagnets are a kind of magnetism that display properties of both antiferromagnetism and ferromagnetism. And because they display properties of both, they're able to be used in applications that would typically be restricted to only one kind of those types of magnets, while also allowing you to deal with some of the roadblocks of ferromagnetism and antiferromagnetism. So because of this, it opens up a lot more avenues of research and kind of expands the possibilities for what we can actually do with magnetic materials. And this is just the sources that I used, and that is all.